It's 3 o'clock, so let's get started again. So there are a couple dates coming up pretty soon. So assignment 3 is going to be due on Sunday, on the 5th, and I just posted assignment 4. So, and I'm pretty much going to stick to the dates that are on the current schedule on the site. And so you can expect that the midterm will come out next Wednesday, and then it'll be available for a week. Okay? So any questions on the schedule as is? Okay. So I just posted assignment 4, so let's take a look. So basically, you'll be doing a variety of problems, so it's not just all about backtracking or all about algorithm design. It's just a hodgepodge of problems, basically. So you're still working on the n-queens problem for assignment 3, but it turns out that there is an explicit way to, for any n, possible n, you can print a valid n-queens solution without having to do backtracking. So assignment 3, I want you to do backtracking, but here I want you to do a well-known theorem which allows you to construct one straight away. So I have a table here which says for all possible values of n, what the design of the solution is. So like here, like for n to be, so does anyone know what a residue class is? So the basic idea here is that the way it's written is that it's if you divide n by 6, the remainder will be 1. So, or it'll be 5 in this case. So this handles the case when you divide by 6, the remainder is 1 or 5. So let's just take the first example would be 7, right? If you divide by 6, there's 1 remainder. So you would place 1 queen at 7, 1 at row 7, column 1, and then you'll continue doing more, all the other possible queens with basically the results from this paper that I cite here. So basically you'll be implementing the results of the paper and then seeing what the queen results look like. All right, so on input this integer n, I want you to output a valid grid. Okay, pretty simple. I have the table there. Should be pretty easy to implement. All right, so the next one is Project Euler 18. So we're starting to move ahead a little bit in the Euler problems. So what is problem 18? So I have it right here. So the idea here is that you have this triangular grid of numbers. So there's one number, say 75. It actually doesn't matter what the numbers are, but all that matters is that there is some number like this. So the first row has 1 number, second row is 2, 3, 4, etc. So what I want you to do is, so like in this really small triangle, what they highlighted is the path from, in a sense, path from the top number descending down in such a way such that the sum along the path is maximal. Okay? So starting from 3, there's no other way to get down to one of the numbers on the bottom that has a higher sum. All right, so what I want you, what the problem is about is, given this much larger triangle, I want you to find the same answers. Something that starts with 75 and then goes all the way down in some way, such that the sum is maximal. Okay, it should be pretty straightforward. All right, it turns out that we haven't gotten to this, but there's a dynamic programming approach that makes this problem a lot faster. So if you have a really fast solution, I would encourage you to try problem 67, although it's not part of the assignment. But it's basically just a much larger triangle. And if you do the straightforward way, which I expect everyone will do, this problem, this particular problem 67 will take a really long time. I actually think, yeah. It would take over 20 billion years to check all possible paths. Yeah, so there is a much faster way to do it than...
Well, on 18, we're not allowed to manipulate the triangle anyway, right?
No, not in this case, yeah. Yeah, yeah, good point. Yeah, it should be this triangle as is, yeah. So any questions about 18? All right, one more assigned problem. So I want you to be able to start working with using Network X. So Network X was the library I talked about last time, which was modeling a graph with vertices and edges. So we talked about complete graphs, right? For some number of vertices n, all possible edges exist between those vertices. So some applications require knowing the number of what are called triangles. So 3 vertices with 3 edges, so it is a triangle. So what I want you to do is to take as input in whatever format you want, a graph. So some representation of a graph, it doesn't matter what format you use as long as you give me a format. And I want you to, when given that graph, output the number of triangles. So then the number of those 3 vertice triangles in that graph. Okay? So that should also be pretty straightforward. Any questions on that? So you'll install Network X on your system and then play around with using Network X there. All right, so as extra credit, I have problem 107 for Project Euler, so really far jump ahead. So what this is basically you're given an undirected graph right here, which has some weights on the edges. So I didn't talk about weights, but basically you can assign a number to each edge in the graph. And so whether that be some kind of cost or weight or distance, some kind of measure. And then they print out the adjacency matrix of the graph that they showed above. So what they want you to look at is, I want to be able to remove as many edges as possible from this graph such that the network still remains connected. The most amount of edges I can possibly remove so that it remains connected. But the thing I want to do is, so once I remove all possible edges that I could while still making this connected, I want the sum of the edges on the graph still there to be as low as possible. Okay? So if I had, say, like this edge 21 in there, but I could remove some other edge, but every other edge here is less than 21, so I can't insert 21 in there. Okay? We'll actually talk about this problem after this assignment is due, but it's a really well-known problem, but I want you to figure out how you would be able to approach this. Like, what edges would you keep, which ones would you remove, etc. It's actually quite difficult to do it on your own, so that's why I made it extra credit, but if you can solve that problem, that would be really good. All right, so any questions about that, the assignment at all? All right, so just looking back at due dates, so project proposal due Monday is still due Monday. So any last minute questions about the project before we leave it? So if you have any questions, feel free to send me an email. If you want to reserve a topic, feel free to send me an email. I think that's it. So, oh yeah, the course withdrawal deadline is, I guess, on Wednesday of next week. So I guess before you have to withdraw from every class. So if you want to withdraw from the class, then that's the deadline, just letting you know. Okay, I think that's it. So yeah, so we have been talking about graphs, right? So we went through a lot of terminology about graphs, about trees, connectedness of graphs, paths, cycles, complete graphs, whole bunch of things, right? So what was the main motivation for studying graphs that I mentioned last time? Yeah, so find some correlation between some entities, right? I have a vertex for each entity and an edge of some kind that has some relation between the entities. And so what do I want to know about the graph? What's one thing I want to ask the question about a given graph?
The longest, shortest path?
Longest, shortest path is one, whether the graph's connected at all, whether what the distance is between two vertices, a whole bunch of other things, right? So that's the question we're going to be asking now and trying to hopefully answer. So the idea here is we want to explore a graph in some way. So we want to look at the structure of a graph, right? This graph could be really large, could be really complicated. I want to answer some questions about it. So the main thing we want to know is how are vertices connected to each other, right? Obviously, if a graph is connected, then every vertex is connected to every other one via some path, right? But maybe I want to ask the question, like, what's the average distance between any two vertices? That's an important question, right? There was some work done on figuring out like the average distance between Wikipedia articles or internet websites via links to other websites, things like that. So you can see like how compact or how spread out the network could possibly be. One example, like in your assignment, is to find many small cliques in the graph, right? So I want to ask the question, how many small cliques are there of size 3, size 4, any number, right? So that's an important question we might want to know. Or maybe how many cycles are in a graph. That's also an important question. Oh yeah, see if there are any cycles at all, right? Because some algorithms work a lot faster if there are no cycles versus if there are cycles. So what do you think is a good idea to start looking through the structure of the graph at this point? Well, we're given a general graph, right? So at this point, it would make sense to look at any arbitrary vertex, right? It doesn't matter what vertex we start with. For instance, like if we want to look at whether an undirected graph is connected, it doesn't matter what vertex I start with, right? Because if it's connected, then no matter what vertex I start with, I'm going to explore the whole graph anyway. So it actually doesn't matter where we start looking here. So how do we look at the structure of the rest of the graph? We actually kind of talked about it last time. Well, so how did we talk about finding cycles in the graph? Right, so we had some way to get back to a vertex we've already seen. So how did we approach that? We started somewhere, then we branched out. Then if we ever found somewhere where we have seen that vertex before, then we found a cycle. So I'm not really going to be looking for cycles here, but I like that branching idea to explore the graph. So there are basically two very well-known algorithms that we're going to be covering now about searching a graph and also finding the distance from a given vertex to every other vertex at the same time. So they're called breadth and depth for search. So we're going to do breadth first. And they actually do somewhat related tasks. So let's talk about this one. So let's look at what vertices I can reach from a start vertex V. So I'm going to find some arbitrary vertex in the graph. I'm going to call it V. And then I'm just going to see what can I reach from here. So what's the idea? We're going to do this branching thing. So I'm going to start at V, look at every possible neighbor I can reach in one step, in traversing one edge. Then I'm going to mark all those vertices. Then I'm going to branch out again and again and again until I hit every vertex. Okay? If I don't hit every vertex and I've marked and I can't go anywhere else, then there's some vertex I can't reach, which means the graph is not connected, right? So this essentially is what we want to do. We repeat until the entire graph is visited. But that's kind of contrary to what I just said, right? There may be some vertex that is not reachable, right? So what do? What we do is we go as far as we can. If there's some vertices left, we start over there, All right. So what we'll be forming is a bunch of trees. So we'll have one tree from where we start, then we may generate other trees. So for the vertices that aren't connected to what I started with, that's going to be another tree. I'm going to go over all this in a bit, but basically we're forming trees starting from where we are in terms of like the path that we took to visit those vertices. So the way we're going to explore the graph is we're going to have three classifications of vertices. Vertices we've never seen before and we're not currently considering. So those are the white vertices. So white means pretty much untouched. Gray vertex means that we're currently looking at it, but we haven't explored all of its neighbors yet. And black means that we have visited it and we considered all of its neighbors. Okay, so these are going to be helpful for figuring out, say for cycles, like if we've seen a vertex already. So let's say that we're looking at a white vertex now, which is going to be gray, obviously, because I'm now going to start considering all of its neighbors. So if we look at its neighbors and we see a vertex that's black, then I know not to go that way because I've already considered it. Right? So if we are at a gray vertex and we see a black vertex, we found a cycle. Right? So and we also want to know the distances from vertex V. Right? That may be important to know also. So here's the algorithm. So I picked this arbitrary vertex V for my graph G. And obviously any vertex works here. So for all vertices other than V, I haven't explored them yet, right? So their colors are white, right? I haven't seen them before. And I'm going to set their distances to be positive infinity. So this is actually what we do classify in terms of distance is if the vertices are connected, like there's a path to go to them, then it's some distance, obviously. But if they're not connected together, so there's no way to get to that other vertex, then we consider that to be positive infinity distance, because there's no way to get there. So initially I just say every vertex is unreachable. If I find some way to reach it, then it has some distance. All right. So since now we're going to start considering all of V's neighbors, I'm going to set its color to gray because, and once I'm done considering all of its vertices, I set it to be black. So the way that we're going to model what vertices we're considering at a given time is with a queue, right? So last time we talked about this frontier, right? So the queue is basically going to hold all of those vertices. It actually doesn't matter if it's a queue here, but what's important is that I can take off a vertex in constant time and add a vertex in constant time. So a queue is actually a very good data structure here, but it doesn't have to be a queue. So queue is essentially going to hold all the vertices that I'm going to be that I'm currently considering their neighbors. Questions so far? Okay. So what we do is, if Q is ever empty, then I have no other vertices to consider, right? Because Q holds the frontier, then if it's empty, then there are no other vertices to consider. So while it's not empty, so it must have some element in it, then I'm going to dequeue one of the vertices. And by dequeuing, what I'm going to be doing is I'm going to be looking at its neighbors, right? Because once I consider all of its neighbors, it's not on the frontier anymore. So I'll never add it back to Q ever. So what I'm going to do is I'm going to look at all adjacent vertices to U. So I'm looking at all of its neighbors. Okay? And then if the color of the adjacent vertex is white, that means I haven't considered it yet. Right? I've never looked at it before. So that means that I will be considering that at some point. Maybe not right now, but I will at some point in the future. And then, so therefore, since I will be considering it, I'm going to change that color to gray, right? But because I haven't ever looked at its neighbors yet. And obviously, whatever distance S is from V, I found a way to get to, whatever distance, oh, that's a typo. That should be use distance. Yeah, that should be use distance. Because I want to update distances as we go. So, whatever distance U was from V, the U is the one I'm considering right now, I just found a way to get to S as a distance from V to U with one more edge, right? So that's a way to set the distance. And sometimes we consider the parent of a particular vertex to be the one that found that particular vertex. So in this case, S, another typo, that should be, I should prepare my slides before I teach. Yeah. So here, parent means that we could also reconstruct the path that from the starting vertex V to this vertex S. So essentially, we can reconstruct how we were able to explore the vertices. Sometimes we don't consider this, but sometimes we do. So we are setting S's color to gray because we will consider it in the future. We know what S's distance is from the vertex V, and we know what vertex was able to find S first. And so since I'm going to be considering it in the future, I better add it to Q, because now it's on the frontier. So I enqueue S to the Q. And then once I do every single adjacent vertex to U, then I'm going to set it to black, right? Because I've considered every adjacent vertex. So I'm not going to ever consider this vertex anymore, so I'm going to set that color to black. I have pictures, so I know this is a lot, but I have pictures. So are there any questions on how the algorithm works? So the main idea is maintaining this frontier and then iterating over this frontier and looking at all of their neighbors as we go, and then setting the colors as necessary.
So that Q that you made with V, that's all of V is adjacent points, right?
Yes. So let's look at the first iteration. So at the very start, the Q only has one element, one vertex, right? So I'm going to look at every vertex adjacent to V. And then after the for loop for the first time, I'm going to set V's color to black. And now the Q has every adjacent vertex to V now, right? And then I just dequeue one of them and then work with that vertex, and enqueue is necessary. Second one, enqueue, and then so on until I explore as much as I can. Okay? Cool, so now I have a picture. So I have this undirected graph with 8 vertices and I think 4, 5, 6, 7, with 9 edges. Cool. So just as a quick quiz, I guess, anyone spot a 3 clique? WTX? Does anyone see a 4 clique? That's not a 4 clique, right? Because not every single possible edge is there. Yeah, so a clique means, a 4 clique means every edge is present. So there is no 4 clique. Yeah, because what is a 4 clique? For a 4 clique, what do we need? Obviously we need 4 vertices. But what are their degrees? They all have to be 3. So let's see, we have W is a vertex of degree 3, T is a vertex of degree 3, X is a vertex of degree 3. Are there any others? Oops. Yeah, so it turns out we only have 3 vertices of degree 3, so we definitely can't have it. But even if we do have 4 vertices of degree 3, we might not have a 4 clique. So we definitely don't here. So, all right. So what we're going to do is we're going to start with S. That's the arbitrary vertex I chose to start from. So it was V earlier, but it's S here. So I'm going to set my distance to 0 for S because the distance from S to itself is 0. So Initially, I have, well, in a sense, I have set the distance to every other vertex to positive infinity, but you can also think of it as uninitialized distance. So, and my Q is the frontier right now, so S is the frontier right now. And so now I'm going to dq S and then look at every single vertex adjacent to S, right? Which happens to be W and R here. So Q will now have W and R. It doesn't matter what order these are added as long as they're all added, right? So S, since I've considered all of its neighbors, now is color black. And I haven't considered R and W's neighbors yet, so they're colored gray. And obviously everything else is white still. And also, I've updated the distances of R and W to be 1, because they're one edge away from S. So if we iterate again, so W is at the front of the Q, so if I dq W, now I'm going to look at all of its neighbors, which are T and X here, right? And since once I do all of W's neighbors, I color it black, and I update T and X's colors and distances. So W's distance was 1, and so since T and X were both white, I update them to gray and update their distances to W's distance plus 1.
The distance is from the original vertex?
Yes, yeah, from the original vertex, yeah. So it's completely arbitrary, obviously, but yeah. So now since I dq W, now the next vertex to dq is R. So now I look at that one and I update the distance on V, which will be the distance of R plus 1 and its color. So we do it again for T. So obviously I'm going to update U, but what's going to happen to X? Am I going to do anything to X? No, because we look back at the condition, we want to look only at vertices we've never considered before. So we've considered X before, so I'm not going to touch that vertex. Oh, R's at the front of the Q, yeah. So I'm going to update R and V as before, so T is at the front. So I'm going to update U only. I'm not going to update X. And update U's color. X is at the front of the Q, so I'm going to update Y. Obviously, V has no white adjacent vertices. So what's going to happen to V? It'll be DQ'd, obviously, but what's going to happen after that? Well, it has no other, it's going to iterate through all of its neighbors, right? It's going to look at R, but R's color is black, right? So I'm not going to touch that one. So there are no others, so I'm just going to update its color, the black. And same thing with U, because it has no white adjacent vertices, so I'm going to update its color to black, and same thing with Y. And since the Q is empty now, I have nothing else to consider, so we're done. All right, cool. So any questions about that?
I'm a little confused by the distance.
Yeah. Yeah, so I don't have anything on the edges, so what distance means is I chose that vertex S to start with, right? So distance means the number of edges traversed to get to that edge. Sorry, to that vertex. It's the shortest number of, it's actually not the shortest, but it's along this path I chose that happened to generate this. It is the distance from, in terms of number of edges. Yeah. It actually is the shortest number of edges from each of the vertices. But anyway, any questions on this? All right. So, all right. So, because I've been talking about network X a lot, I want to do an example with network X. So, instead of implementing this whole algorithm, which I really don't want to do, there are some awesome functions in network X that we can use. So there's a function called isConnected, which says that it'll return true if the graph is connected. It'll return false if it's not connected. So this is exactly the same thing as we did last time with this Facebook data set. So the only thing I've added is this is connected thing. So hopefully we will see that the graph is connected. So Python 3 parse Facebook. Oh, so it says true. So that means our graph is connected. Nice. So because our graph is connected, we can do this breadth first search idea, right? So we can start at a given vertex, doesn't matter which one, and we can look at how we explore the graph. So there's a handy little method called a BFS tree with a G and a starting vertex. So because when we read the file, it's just string space string. It's not numbers. So I should specify that I'm looking at a particular vertex, and one of the vertices names is 0. I just arbitrarily pick 0. You can pick any one you want because it's connected. All right. So so we can just take a look at this. Print H. And so what BFS tree returns is the tree which was generated through the breadth first search algorithm. So what do I mean? Well, the way we generated these numbers, right, was through the parent pointer thing. So if we look at what the parent pointer of, say, R is, the thing that found R was S, right? The thing that found V was R, the thing that found W was S, the thing that found T was W, the thing that found X was W, and U was found by T, Y found by X. So we can think of this as a tree, right? So we can think of it as S is the root, with the next layer being R and W, and the child of R being V, the children of W being T and X, and the one child of T being U, the one child of X being Y. So we can think of that as a tree. So that's basically a way of looking at the graph. We started with X and we looked at the traversal this way. So what BFS tree is all about is it'll return to us this tree essentially. So it actually returns a graph. So I call the graph H. So let's see. I think, yeah, it doesn't print anything. All right. For some weird reason in Network X, it doesn't. When you try to print a graph, it doesn't print anything. So if we look, so since we can't print graphs, it might be a good idea to have some visual representation of what a graph is. But right, the only thing that we looked at last time was with this matplotlib pyplot thing, which we plotted all of the degrees of the vertices, right? We just plotted a whole bunch of numbers, but we didn't plot a graph, right? So it might be a cool idea to draw a graph in like a picture, let's say. So that's what we're going to do here. It turns out that there are a lot of methods in Network X that allow you to draw graphs using matplotlib. So that's what we're going to do here. So what I'm going to do is call an nx.draw of h. And then I'm going to call plt.show. So nx.draw just makes a figure in the background, and plt.show will actually show the figure, obviously. So if we run this, it will take a really long time. Anyone remember how many vertices there were? A little over 4,000. How many edges? Around 88K. So essentially, I'm going to be drawing 88,000 lines on a picture. So I'm going to stop it. And I've actually done a lot of it for you. But the cool thing we might want to do before I show you is we may want to, just as a visualization, make the way that it's plotted, the way that the graph is drawn is circles are vertices with lines attached to the to the corresponding neighbors. So it might be a cool idea to make the vertices that have a larger degree, so more edges coming out of it, to be larger. So the way we could do that is we can find the largest degree vertex and then normalize it. Okay? Normalize all other degrees into, like, say, an array or a list, and then we feed it to the plotting library to draw, and then we plot it that way. So what we would do here is, well, we want to find the maximum, so we just look at max, and the way we get all of the degrees of all vertices is calling nx.degree of g. So what nx degree of g returns is a dictionary, and in the dictionary, the keys are the vertices, and the value is the degree of that vertex. Okay, so it's going to have, say, like vertex 0 has degree 100 or something. So it'll have entry 0 colon 100, and then for every other vertex it has this. But it doesn't make sense to look at max here because it's a key value pair. So I only want to normalize the degrees of the vertices. So to get all of the values of the degrees in this dictionary, we just call values. So this will now just be a list containing all the degrees. And largest now will just be the largest one. So now what I want to do is I want to make a list called node sizes. And so what this is will be a list that will contain the size of what the circle will be when it's drawn. So initially, I'm going to set them all to be 0. So how do I make a list of the number of vertices just zeros, like 0, 0, 0, 4,000 times? So how would I do that?
Use the overloaded star.
Exactly. So 0 times the number of vertices in the graph, which is just the length of the nodes. So basically, I'm just finding the number of vertices in the graph and making a list that contains just 0, 0, 0, 0 that many times. All right. So now I want to update each of the entries in this size list. So what I want to do is basically look over for v in g.nodes. I want to write out to node sizes the size of what that particular vertex v will be. But the thing is, I want to keep the indexing the same. So I want g.nodes returns me the first, say, index 0 vertex. I want index 0 of node sizes to be that, right? So one way we can do this is we can have a counter to be 0 and then update it as we go. But there's a much better way. Anyone know of a way to get, so basically v here is the vertex, but I want the index at the same time. So anyone know how to get the index and the element at the same time? It's a very, very cool function in Python. It's what's called a enumerate. So I feed the thing that I'm looping over to enumerate, and what enumerate returns is index with element as a tuple together. So I can unpack that at the same time. So I can say for idx comma v, so what that means is it's feeding me the index and the element at the same time. So that's what enumerate does. So now I want node sizes of this particular index to be the degree of this vertex v normalized by the largest number, right? So that is just, so to get the degree of a vertex, you call g.degree of v. I actually don't like how inconsistent network X is sometimes because you're basically calling the library function here, but here, when I want the degree of one vertex, I call the instance function. So I hate how it's inconsistent like this, but anyway, g.degree of v will return me the degree of this particular vertex v. And then I normalize by the largest one. So how do I normalize? So let's say the largest one is 4,000, let's say. And I have v to be, v's degree is 100. So how do I normalize that? So I want it to be a number between 0 and 1. Divide by the largest, yeah. So I'm normalizing it. So there are a number of ways of normalizing in general, but what you do most of the time is just divide by the largest one. So it becomes a number between 0 and 1 here. It turns out that this circle is too small, so what we're going to do is we're going to multiply by a constant for each one. So the best one I found was 300, but it's just a constant to add to it. All right. No, I don't want to purchase yet. So I'm going to do this BFS tree again. So I'm going to basically be plotting this directed graph now from the starting vertex 0, and then it's just going to branch out from there. So I want to now feed this list node sizes, which is the size of nodes, to my plotting function. So the way to do that is with a named argument, which is called node size. So node size is a named argument, which is just a list, which tells the draw function to say, hey, I want to draw each of these vertices with this size. So I'm going to call it node I feed it the list node sizes that I just made. All right. So if we do that, it'll also take a really long time. So I went ahead and did it for you. So this is actually what it ends up looking like. And it's actually really, really cool. So so the starting vertex, I believe, is over here somewhere. And each of the vertices, some vertices are larger, some are smaller, and each one is based on how many edges it's connected to. So since this is a directed graph, I think Network X considers it as in degree and out degree. So, oh, what's that? Yeah, so what I'm doing here is the BFS tree. So it's basically, I'll go back as an example. So the BFS tree is just how I explored the graph. So S will basically have an outgoing edge to R and W here. And then R has an outgoing one to V, W to T and X, T to U, X to Y. So it's basically how the graph was explored here. So basically, this is how the graph looks when I explored it using BFS. Okay? So it's actually really cool to just purely as a visualization thing. So you can see like there are a ton of vertices over here, but there are relatively few in the middle. So you can think when we get to the centrality part, we can consider these vertices right here as really important, right? Because it's a lot of the way through this camp of vertices to this camp of vertices is through those. So you can think of those as important vertices. And you can actually see over here, right near the starting vertex, that there's a lot of overlay of vertices. So you may also want to consider, hey, among those vertices, which one is the closest to all of the other ones? That may be an important metric to look at, right? But anyway, this is just a way to visualize how BFS was able to traverse the graph, how you were able to start from a given vertex to get to any other vertex. And since the algorithm doesn't depend on what vertex I started with, I could have started this with any other vertex, and this may look entirely different, right? But the way, because we found out our graph was connected, it doesn't matter what one I start with. All right? So any questions about that? Cool. So now let's look at the analysis of this. So what BFS is doing is computing the shortest distances from this starting vertex to everywhere else, right? So it finds everything it can reach in one step, then it marks all of those. Then it goes to everything in 2 steps, marks those, and it goes through all the rest of the graph. So the parent nodes, like when we looked at our BFS tree, are just basically like a certificate of how we were able to traverse the graph, right? And the way you can write it is that you can write these as directed edges that point back to the root. So from any node, you can just traverse the edges back until you reach the root. Could I possibly get a cycle there? Could I like start traversing back toward the root and I end up visiting another vertex along the way twice? Like, no, why? Because this thing that I just generated is a tree. So what's the property of a tree again? Has no cycles, right? So whether the edge is pointed toward the root or away from the root, as long as it's the same for all edges, you're not going to get a cycle. So there's a unique way from each vertex to get back to the root, right? So therefore, we know exactly the shortest path from each of the vertices back to the original root. Actually, I should say a shortest path. We know of a shortest path that goes from each vertex back to the root. Yeah, we can reconstruct all the shortest paths from each vertex. So now the most important thing about algorithm design in general, what's the runtime? Well, what are the costs of this algorithm? We have to explore every vertex because that's the whole point of breadth first search. We want to explore every vertex, right? That's the entire point. But we explore all possible neighbors of every vertex, right? So what does that mean about the edges? Well, since we look at every single neighbor of every vertex, am I going to ever ignore an edge? No, because every single edge has 2 vertices on it, and I'm going to explore both of those, which means that edge has to be considered, right? So therefore, I must explore every edge. So therefore, I see every vertex and every edge. So that means I must have an algorithm which it runs in time the number of vertices plus the number of edges, right? Because how many times do I see an edge? Well, I see it for each, let's just say the vertices are S and T. So when I look at S, I'm going to consider that edge, right? And when I look at T, I'm going to consider that edge again, right? So how many times did I consider that edge? Twice. Am I going to ever consider it again? Am I going to ever consider S or T again? No, because I'm going to mark those vertices black. I'm never going to visit them again. So each edge, I visit twice, right? So therefore, I have a plus here because I only explore every edge a constant number of times. So the constant's hidden in the notation. And actually, you can refine this to be O of the number of edges, right? Because each edge is connected to 2 vertices. So therefore, the number of edges is the same order at least of the number of vertices. So I don't even need to write the size of V here, but it's just a helpful thing to look at, that you're looking at every single vertex and every edge, right? A constant number of times. Any questions on that? And we also require the number of vertices as extra storage. Why do we do that? Why could we possibly have that kind of extra storage? For the queue, right? Because what could possibly happen? What can happen is I start at a vertex, and it's connected to every other vertex. So I add every other vertex to the queue, which means it has ordered V vertices in it. So I must have, for this algorithm, I must have at most the number of vertices extra storage. I don't need to consider the edges, right? Because I'm just considering the possible neighbors for each vertex. Actually, that's important to note. I'm storing these number of vertices in this queue, but I'm also, for each vertex, storing the neighbors attached to it. I'm iterating over each of the neighbors. Well, this vertex that I'm considering right now could be connected to everywhere else also. So I need to store those vertices. So I must have V possibly plus V possibly, 2V that's hidden in the constant, in the O notation. So I must have order the number of vertices as extra storage. So any questions on this? Okay. So I talked about another famous algorithm called depth first search. So the algorithm we just covered was breadth first search. So what do you think the main difference here is between breadth and depth first search?
Instead of looking at all of its neighbors, you go as far as you possibly can, so it all one.
Exactly. That's exactly what we want. It's another way of exploring a graph. Instead of having this frontier and just building out and out, what we're going to do is we're going to start somewhere and then go as far in one direction as we can until we can't go anymore, then backtrack. Try the next direction from the one we just backtracked to, go that direction till we have to backtrack. So the algorithm is quite similar, but there are a few differences. So we're going to have white color as usual for vertex we haven't seen before, and black when we're done. So instead of using parent pointers to figure out where we've been, we use what are called timestamps. So the time that we enter a vertex, and then the time we actually finished backtracking to that vertex, and then at that point when we can't go any further. There are no other considerations I can make at this point. So it's kind of like a certificate of when you saw this vertex and when you last saw it, and never consider it again. So yeah, it helps us reconstruct the past later. And the main point here that's actually critical is that we must make sure that the timestamps, the start and end time, are all distinct, right? Because we have two timestamps that are the same, then we may have a conflicting path at the end. So we better keep these distinct. So the algorithm is, do I have? Okay, yeah. So here we actually it doesn't matter what vertex we start with again. So what we're going to do is consider all vertices to be white. I haven't explored any of them yet. This timestamp is going to be in the variable time, and the timestamp currently is 0. So what I'm going to do is for every vertex in all of G's vertices, I'm going to do basically this algorithm of going as far as we can and then backtracking with recursion. So if the color is white, that means I haven't considered it yet. Then I'm going to call what is this method, which I haven't defined yet, which is called DFS visit of V. So DFS visit of V means I'm going to start at V and then do everything I can at V. And then once I'm done, then I'm going to mark it a certain color. So I never get back to here again. Okay? So how does the visit work? So I'm going to have the gray and black colors as before. So gray means I'm currently considering it, but am not currently done with it. So I'm going to increment the time so that I make sure that the timestamp is distinct. So now I've started considering V because I guarantee I've never seen it before. So this is the first time I've seen V. So I set its discover time and to be the current timestamp. And at the end, I'm going to set its final. I think I called it final time, or no, I called it finish time. Yeah. So discovered and finished time for each vertex. So now I'm just going to look at each of the vertices in turn that are adjacent to me and consider them one at a time. So let's just say I'm looking at vertex U right now, which is the first one. Then I'm going to go in that direction. I'm going to recursively call on U. Okay? I'm just going to head that direction. I'm not going to mark every vertex at the same time. I'm going to go in one direction, then come back, try the next one, come back, third direction, come back, etc. So if U's color is white, then that means I haven't considered it yet. So therefore, I can go in that direction, right? So therefore, I recursively call on U. And then I go in that direction, and then up until the point where I can't go any other direction, right? So if U doesn't have, let's just say that V doesn't have any neighbors I can go to. Then that means I must backtrack, right? But there are some cleanups we need to make. Well, since I can't go anywhere else with V, I color it black, right? Because there's nowhere else to go. I increment the time to make sure that it's distinct, and I set V's finish time to be the timestamp. All right, so that's just cleanup at the end. So any questions on how visit works? So the main idea is travel in one direction until you can't go any further, then you backtrack. And by backtracking means that this for loop, you can't iterate anything because there's nothing else to... Well, actually, there may be iterations here, but I'm never going to say yes to this if statement. Right? Because if there are no other white vertices I'm currently connected to, then I can't go any possible direction. Right? So I must backtrack in that case. All right. So I know that this is a little bit of a complicated algorithm, so I have a picture. So the way DFS works is the graph does not have to be connected, and it doesn't have to be undirected. Well, actually, it didn't have to earlier, but it works just as well if the graph's not connected or even strongly connected for directed graphs. So what does strongly connected mean again for directed graphs? Strongly connected. In a sense, yeah. Well, the maximum number of edges is the complete graph, but strongly... You looked at my slides. Yeah, so just as a refresher, strongly connected means only for direct graphs. Means that no matter which vertex I start from and end to, there's a path to that way, right? So I can travel from any vertex to any other. So what does weakly connected mean, if anyone remembers? Weakly connected means if you remove the directions on each of the edges, so now it's undirected, the graph that's remaining now is connected. So the undirected version is connected, but not necessarily the directed one, right? So
You say if you remove the direction?
yeah, so like this edge that goes down from here to here, I just make it an undirected edge now.
Yeah.
So I can go either direction. So clearly, if I did this for this graph, it's clearly connected, right? But is this a strongly connected graph? There's actually one vertex where you can't reach it at all.
Bottom right.
The bottom right can be reached from this vertex. See, like you can go down this way. The top right, yeah. There's no incoming edge to that top right vertex, right? So therefore, this graph is not strongly connected. But the cool thing about DFS is it still works with this, and we'll see that in a second. Because if we look at the way the algorithm works, I just go iterate through every single vertex in the set of vertices. It didn't matter whether it was connected or not, and I'm not branching out in this way. So I just, even if we get to a point where we can't go any further with respect to depth first search, I just pick another vertex, even if I couldn't reach it from where I started. So it doesn't matter whether it's connected or not. So because the algorithm just says iterate through all vertices and do this visit thing, it doesn't matter where I start, but let's just say I started at this top left vertex. All right, so I increment that timestamp thing. So I'm going to have two values for every vertex, the discovered time and the finished time. So the discovered time for the start vertex is 1 because I add 1 from 0 to be 1. And then once I'm done doing the depth first search, I'm going to set the finish time on this vertex. So I haven't explored anywhere, so that's why nothing else is colored anything. And this vertex is gray. Although it's not gray here, it's supposed to be gray. But anyway, so let's just say I chose that direction, this particular direction. I could have went down to the middle vertex on the bottom row or the middle vertex on the top row, but let's just say I chose that direction. So I colored that vertex to be color that vertex to be gray. So now what I need to do is I need to look at each of this vertex's neighbors, and I need to go in that direction, recursively calling myself. So it turns out I'm just going to pick this vertex because I could have went with this one also, but let's just say I picked this one. So I'm just going to keep going in this direction until I can't go anymore. Right? So let's see. We're at this vertex right now. So does it have any adjacent white neighbors? No, because you may say, well, it has this one, right? But the direction is what matters here, right? So let's see. It has a gray vertex as a neighbor, so there's no white vertices to consider. So that means I'm going to check that one. It's not white, so that must mean I must backtrack. And increment my timestamp and set the finish time. So I set the finish time and make it black. So now I backtrack. Since I can't go anymore with this vertex, I backtrack to the one I was at. And does it have any other white neighbors? Yes, it has this one. So I go to this vertex, and I set its start time and make it gray. Does this vertex have any white adjacent members? No. So I set its finish time, convert to black, go back to the vertex over here, and does it have any white adjacent members? Nope. So I set its finish time, and then since I guess I skipped one. This vertex now had this adjacent white vertex, so I go to there and increment the timestamp. And then, does this vertex have any white adjacent members? Yeah, this one. So I go to that one, update the timestamp. This one doesn't have any white adjacent members, so I make it black, and then I keep going. This one didn't have any more, so I updated it. And then since the starting one didn't have any more, I updated it to black again. But I have 2 more vertices, right? So now, since the starting for loop said loop through all the vertices and then do this visit thing, it'll just pick one of these remaining ones until I've exhausted all the vertices, whether it's connected or not, right? So let's just say I happen to pick this top vertex, and since it has a white adjacent member, I do its thing again. Then, since this one doesn't have any white adjacent vertices, I update and I update. And now, since all vertices are black, I'm done. Whether it was connected or not, it didn't matter. So I updated every single vertex here. And now the timestamps will tell me how I was able to explore the vertices through this start vertex. But wait, you say, let's just say I know a way to get from here to here to here. I know that path. I know the one from here, the starting one to here. I know the ones from here to here. But what about these last two? I have a starting one right here, but I can't reach these ones. But I still marked them black. What happened? I actually did the algorithm again, basically. So I made a tree, like the breadth first search tree, but I call it a depth first search tree for the vertices over there. But I made another depth first search tree for the 2 vertices over here. So I'm going to actually have a whole bunch of trees, possibly. So what do you think a lot of trees are called? Forest. So that's what we're actually computing here, a shortest path forest. So I'm computing shortest paths, but I'm going to have a whole bunch of trees if the graph was not connected. If that graph was undirected, then clearly it's connected, so I would only have one tree. But since it wasn't strongly connected because it's directed, I have multiple trees here. So I have a forest. And there's really neat algorithms on forests if you want to pursue that for a project. But a forest may have exactly one tree and may have many trees. A forest is a collection of disjoint trees. So I have a tree over here, a tree over here, but there's no way to get in between them.
So like on the previous slide,
Mhm.
does that mean this one has two trees?
Yes, so it would have a tree that's rooted at this starting vertex over here and another one over here. Actually, a really cool term is, a really cool term for a tree is called an arborescence. So that's just another term, but you had a question?
Why would that, can you go back to the slide?
Yeah.
The first one be a tree because it has a cycle, doesn't it? Back to itself.
The tree of the paths I took. There is a cycle, right? But of the paths I took.
Okay.
Yeah, no, I'm only considering the paths I took. But clearly there is a cycle here. You're absolutely right. Any other questions on that? All right, so let's look at the analysis. So the timestamps are really useful. They help us figure out when the vertex was discovered from whatever route we are considering, and the time when we were done visiting that vertex. So it helps us make the shortest paths, kind of like how we did for breadth first search. So what's the running time? Well, I'm considering all vertices, right? That's because the first algorithm already did all vertices, so at least the number of vertices. But what about edges? Well, I'm basically doing the same thing again. I'm checking if the vertex was white, right? And if it is white, I go in that direction. But if it's not, then I don't go that direction. So how many times do I consider an edge then? At most twice. Maybe only once, but at most twice. So I basically have the same running time as before. It's essentially the same thing, but just doing the approach is just a little different. Going in one direction versus just branching out with breadth first search. So we look at each vertex. Even if it's in a different tree, like we had those two trees, we may have a different tree, but we consider those edges also, and vertices. And we look at every possible edge because it may lead to a vertex of any color. So we have the same running time. Questions on how that worked?
How would you know, so when you're running this, how would you know you have more than one tree? Do you know how the time, like, the time basically continues, right?
Yeah.
How do we know if it's more than one tree?
Yeah, so if you look at the running times, this one started at 1 and ended at 12. So any vertex that starts after 12 can't be in the same tree, right? Anything that's not between 13 and 16 strictly, then it can't be in this tree. So it helps us not only make the shortest paths, but it also makes us the forest at the same time. Isn't that so cool? Just simple timestamps was able to reconstruct this. I get goosebumps. Yeah. So any other questions on this? Okay. On to Dijkstra. Dun, dun, dun. So this is like one of the biggest hammers in all of algorithms and graph search algorithms. So anyone heard of Dijkstra? Yeah, so he got, I forget what medal he got, but he's one of the most famous computer scientists because of this algorithm that I'm gonna describe to you. So it's just really cool and how easy it is to understand, but how how different it was from breadth first search and depth first search, and in their approaches. So, what do you note about the edges here? In terms of the distances we computed. Like say, let's look at this vertex 8 and 11 from 1 and 12. What was the distance we computed for that?
7.
This isn't the distance, it's just time. So it's 1, right? So do you think all graphs have edge weights of 1? Like a number associated with each edge of 1? No. You can think of that like for a road network for Google Maps, right? There's some distance attached to between two cities along some highway or something. So there's a distance set to each edge that may be different than every other one, right? So this algorithm does not work for any other edge weights other than 1, right? Because let's say that, just as an example, so let's say that this edge right here has an edge weight of 5, just picking off the top of my head. This down edge weight has length 7. No, what's an easier way? Yeah, let's say this one has 5, this one has 1, and then this one has 10. This one from 1 and 12 down to 5 and 6. So I have one that's 5 and 1 versus 10. So in this shortest path tree that I made, which edge did I consider? From 1 and 12 to, did I go the 8, 11 route to 5 and 6? Or did I go straight there? Well, I must have went straight there, right? Because 8 and 11 timestamps, 5 and 6 are not in between 8 and 11. So I couldn't have went this way. Well, I did, yes, okay, so you're right. So let's just say I have 5, 1 and 2 versus 5 and 1. So the way through this way is total weight 6, and then this one is total weight 3. So, or maybe if we have a longer edge weight here, that's the one we actually considered. But the one that could have went through here was a shorter edge weight in total. So we actually did not get the shortest path from 1 and 12 to 5 and 6, even though there was a shortest path already existing. So basically what Dijkstra's algorithm is all about is having an arbitrary set of, it actually is positive edge weights. So as any positive edge weight on the edges, we can run Dijkstra's algorithm to get this shortest path forest. Okay, so what it does is shortest paths from between vertices. So the way that these are described in the literature is single source shortest paths. So single source means that I start at one vertex and then I find the distances to everywhere else. So there are some algorithms like Floyd-Warshall which are about all pairs shortest paths. So it calculates all the pairs shortest paths there. But here is only single source shortest path. We actually have a worse asymptotic running time here. So why can't we just run breadth first search? Well, breadth first search determines the distance of how far a vertex is away from the number of edges, not the actual weights on the edges. So it's independent of the actual weights. Yeah.
When you say weight of edges, the distance?
It's some number attached to each edge. So it could, in some cases, mean cost. It may be distance. It may be whatever metric you want. But it's just some number attached to each edge. Yep. Any other questions on that?
Is that kind of like when you're looking at a map and you have different routes, and one route's too long and the other route's, you can like say one route's like a mile and the other route's like 2 miles? Is that what kind of related?
Yeah, so that's essentially what Google Maps does is single source shortest paths from where you are to not every single place in the country because that would take forever. From where you are to your indicated destination. So it looks at, maybe if I try this way, it will give me less time. So obviously, it may be a good idea in case of Google Maps to associate on each edge to be the amount of time spent there, not necessarily the distance, because you may have a shorter distance traveling among like a neighborhood route versus a freeway, but the neighborhood one will take longer because you're going slower, obviously. So in that case, it might be time, but it's some metric. Breadth first search is equivalent to Dijkstra if all the edge weights are 1, because in that case, if all the edge weights are 1, it's just counting the number of edges, essentially. It's the same thing, but not for any other edge weights. So how do we count for edge weights? What we do is basically a little bit of a modification to breadth first search, or depth first search if you want. You maintain the shortest distance so far, and then let's just say that I found a particular distance, like say 100 for a vertex. And then I keep exploring, then I find a way to get back to here that says, this vertex I found over here has distance 30 from the source, and this edge has weight 20. So 30 plus 20, that's a shorter path, right? So I update this guy's total distance to be 50. So I maintain the shortest distance so far for each vertex. And then I update if I find a shorter one until I have exhausted the entire graph. Okay?
That's why it has a bad runtime.
Essentially, yeah. If we see a way to get to this vertex with a smaller shortest distance, then we'll update. So I'm not going to get to that today. So are there any questions about what we've covered today? Any questions on anything class related, like the project proposals due Monday, assignment 3 is due Sunday, and assignment 4 is out? Any other questions about that? All right, I'll see you next week.